CR 听得到吗？
Hello， 可以。
好，谢谢。Yeah, we are ready.
Okay. Let's go. So, yeah. So last part for today's presentation. So it's a bigger one. It's about the foundation from load out to the float off. In the same fashion as the topics of this morning, first we'll be looking at the stakeholders timeline and selections of assets, then operation preparation of these different stakeholders, and then the execution of the work. So therefore, the load out and float off, there are more of stakeholders compared to this morning, and that will obviously increase the complexity of the operation. First, we will have the assembly facility. So your marshalling location depends on your supply strategy, but we will assume that it is a location where your foundation is dry stored or has been finally assembled at the facility, and this facility has quayside access to the sea for the HLV company. Second stakeholder, focusing on the loadouts, the SPMT supplier. So we'll see what they are doing. So they will be the enabler to bring the foundation from the assembly facility onto the HLV. Then we have the HLV supplier or contractor. They will cross all three steps of this methodology. So from loadout, transportation to float off on site, and irrespective of the distance of your float off site, you will always have to go through this three stage. So you will always have a transport stage that has its own requirements and calculations associated. Then, similar to the topics of this morning, the foundation designer will have to be involved from loadout to float off in a similar fashion. Then for float off only, we will need an offshore vessel spread. Can be AHTs, basically we will see some vessels to make the station keeping of the foundation and help with the float off from the HLV. And last, same MWS might be required, depends on your stakeholders' requirements, but basically they would work across the different phase from loadout to the float off. I promise it's the last time you're seeing it today, but still the same logic. Today, these operations, even the float off, they are operations that have a good regulation and rules frameworks. They are good understanding of this loadout and float off operations, even for a floating wind foundation. So the regulation rule specifications are fairly well set. The overall planning benefits from wide feedbacks from existing operations, and so we have a good understanding on how the operation is working. Design brief and design basis same. There is a good understanding, and then we will have to basically ensure of the loops between the engineering and design with the operation procedure. We are closer to what we had for the mooring, which is today there are sufficient expertise from the different operators to provide procedures feedback, to provide feedbacks from operations. And so the engineering can start with already some existing data or some reference points for designing and getting the design suitable for operation. But this time will still be the critical time and the critical loops to be able to coordinate the work and progress in the planning. In terms of global timeline, same as for the floating to floating, we are talking about a range of durations that are in the year or years before. These are operations that need proper planning, proper selection of assets, and for which the operation engineering is going to be critical. The operation engineering will depend on your foundation and on your engineering. So it has to be incorporated in the design of your asset as early as possible. And we will see there are some impacts when you perform loadouts, when you perform floatouts, that can be directly within your primary steel. So as early as possible, you will need to understand the interfaces that you will face during loadouts and transport. In the months preceding the operation, same, you will need to have finalized your operation engineering. There are significant amounts of steel to be fabricated to enable the operations. You will need some support, some grillage, some C-fastening, some guides, some specific reinforcements on the HLV. All this, they will have to be engineered, and you will need a range of months to start the fabrication of all this. The biggest component in terms of weight being usually the grillage and C-fastening components, which is obviously depending on your foundation and the HLV selection. Within the weeks before, you need to have obtained the approvals from the stakeholders like the MWS. You will mobilize the HLV to the assembly site, and you will start installing any temporary steel on it. Usually, you start with the grillage. It can be a significant amount of work that you will have to do at the site. And then within the days before, you can start preparing your SPMTs for the operation, mobilize them, assemble them at the assembly site, and test the SPMT configuration. And then you're ready to start. When looking at asset selections, the first asset that needs to be looked at is your HLV, or your semi-submersible vessel or barge. The difference between vessel or barge is because the vessel will have its own propulsion, the barge will need to be towed with its own towing spread. The few criteria that you will need to meet, one will be the loading capacity of the vessel. So you will see the vessels that are rated in terms of their ability to load cargo. In terms of cargo density, your foundation is actually quite low compared to, I don't know, like oil and gas modules, for example, that have lesser interface points and concentrate a lot more of the loads. But still, one of the main limitations and one of the driver that you will have for your selection of the asset, it's going to be the deck size and related deck strength. The deck size, when you're performing transportation that's going to be very short, if it's just about bringing the foundation offshore to do a float off, because you basically use it as an alternative of lifting to launch your foundation, then you can take, let's say, very narrow weather conditions, and you can afford to have your foundation, for example, being wider than the vessel, or having some temporary steel to support the broad footprint of your foundation. Because that's the main issue that we have with semi-sub foundation, is about just their size and their footprint. It's going to be very difficult to get an ocean tow or ocean transportation approved with a foundation that exceeds the breadth of the vessel by too much. You can have a little bit, but it cannot be too much. It will be subject to green waters, it will be subject to a lot of design conditions, and sometimes it can be even just not approved for the vessel, because too broad on a narrow vessel, you actually run the risk of having the foundation contributing to the water plane and stability of your asset in case of excessive roll in high conditions. Then, because we are aiming at float off, obviously it is a semi-submersible asset, so you will look at the submersion capability. The submersion capability is driven by how deep your vessel deck can go underwater. And we will see there's a small calculation summary. Basically, you need to go as deep as needed to meet your foundation draft, plus clearances, plus the grillage. So you will need a significant water depth to operate the vessel, and the vessel needs to be able to cope with that. Then availability and day rate, same as for the other ones. It's always something that you have to take into consideration. In this case, the, let's say, semi-submersible vessels are, let's say, for local float-off are widely available. You will find sufficient vessels that have the capacity to do that. Now, if you're looking for a scenario where you are installing and transporting your assets further, which means you need a bigger, broader vessel, there you will have limitation, and the number of vessels that can actually house a 60-meter foundation breadth is limited. The primary objective when selecting a vessel is that we are not too worried about the global capacity of the asset to carry. Even if your foundation is 5,000 ton, I think you're 3,000 ton on primary steel, so maybe 4,000. That's way below the capacity of this vessel. But you need to work in a model where you should be able to pick up the foundation without having to modify the HLV to satisfy like local deck strength capacity. So the interface between your foundation and the barge is going to be critical. What you define as the grillage between the two is what's going to bring the load from the foundation down to the barge. You want to minimize it because it is extra steel, it is extra fabrication time. But not having it or a bad design of grillage basically just brings the problem further down, and further down, it's your vessel. We'll see, we don't want this to happen. So to maintain a cost, let's say at a lower level, we try to select assets that are basically strong enough in terms of deck capacity and compatible with your foundation. Another reason is that here you're looking at a one-off, for example, float-off. You're looking at bringing once the unit offshore. But when you have to repeat this model in a more industrial or commercial philosophy, you might not be provided the same vessel all the time. So you need to be able to adapt your grillage and to make sure that you're not reinforcing every vessel that the contractor is going to send to you. Because you're not going to keep his vessel parked waiting for all the foundations to be ready. You will launch some of them maybe in waves. And after that, you're not always guaranteed to get the same asset back. So when looking at the HLV, it's very straightforward. What we are looking for is, as we said, the cargo deck. So in this case, here you have some buoyancy towers, but in most of the assets, these buoyancy towers, they can actually be removed or shifted. It means the cargo deck in this configuration typically will only give you access for a loadout alongside the key. So you will have to have your key side along the vessel, and you will load your foundation in this direction. It's not always let's say, the best in terms of managing the ballast and managing the vessel. It is sometimes more efficient to actually just have these buoyancy towers shifted or removed and have the vessel with the stern against the quayside, and you load out just at the stern of the vessel. Because in terms of managing your global bending and the ballast of the vessel, it's a lot more straightforward. and you basically just bring your SPMTs at the aft here, adjust your ballast, and you're done. So when on the side loading, there is a bit more complexity in the management. The next thing that we look at is the submersion line, as we said before, is the ability of the vessel to go underwater. So this one on the white marine, the line is indicated here. So basically, your vessel will offer you all this clearance to satisfy your foundation draft plus the bridge plus the clearance. So these are the main two parameters that we look at. When I was mentioning the availability of assets, so here you have a broad picture, very broad picture of HLVs. And you can see that the capacity goes, I mean, nearly it's multiplied by 5. If you take the biggest one, which is the Boca Vanguard, which is overkill for your foundation, let's be clear. But down to smaller vessels from the SIL family, for example, this is the total lifting capacity. So you can see that even with the smallest HLV assets in this table, the margin that you have with your foundation is quite broad. You could even consider, in the event where you're doing an actual transportation with a voyage, and not just a launching for a float off, to have more than one single foundation on the vessel. It's only a matter of deck space available. As I said, the main constraint that you will meet is how much breadth you can provide on your vessel. So here, for example, 60-meter breadth is what allows you to support the 3 columns up to the side shell, but you still have some of the foundation that will be overhanging. Roughly half of your column diameter is over the water. As we said, when it is about just a float-off operation, it's not a problem because you're not sailing in unrestricted condition, going very far. It will become a problem if you try to go further and actually have a transportation or a voyage case for the vessel. And this is the factor that's actually going to limit the most the selection of the vessel, is the breadth of the transportation. So on top of selecting the HLV, the selection of the quayside or the marshalling location, call it as you want, will also have its set of constraints. Main one being the equipment that are already existing on the quayside. So we are talking about the availability of fenders, for example, that can be permanent or temporary fenders on the quayside. But also the bollard beaks and their ratings, the exposure also of the key is a factor that can be taken into consideration, especially when doing SPMT loadouts. Typically, if you have a lot of passing traffic alongside the key, or if you are very exposed to wind, wave, or currents at this location, it will have an impact on your operability. And you will have to basically hold for longer periods of time. Still in the quayside selection, one factor is that we need to make sure, and because of the footprint of this foundation, we need to make sure that there is sufficient space and access to the quayside to do the actual loadouts. A lot of quaysides are, let's say, able to give access to vessels when they are moored alongside on the quayside. They don't necessarily have a clearance that allows the full structure to pass on SPMT. So sometimes it will require some, let's say, some changes in the way you will have your wharf, but it means to have nearly 80 to 90 meter clear quayside to perform the operation. And another factor is that while at your fabrication location, you will have a grillage supporting the foundation during fabrication or during assembly, you will need to consider that your SPMTs once they will take the load, they will transfer the load to the quayside. And for the whole route from the fabrication or assembly location to the vessel van, you need to satisfy the minimum ground bearing capacity, knowing that if you load at near full capacity modern SPMTs, you are imposing 10 to 14 tons per square meter. This is a requirement which, yes, for some assemblies area, for some quaysides, we can find in, I would say, not a large number, but a significant number of port facilities. But in this range, 14 to have it over the whole area and the whole route to perform the loadout, usually there are facilities that have been built having loadouts in mind, so skiddings or SPMTs in mind. Just it works. Let's show you this one. No, I'll show you. It's a VR view of the basically of this picture, just to give you an idea of the scales of these foundation models with the vessel and all that. But it's not opening on the link of the PowerPoint. So if you're interested, I can show you later. So on top of so that was for the last let's say large asset selection and basically where you have to choose your execution marshalling, your marshalling location. Now, in terms of operation preparation, so we've seen there are many stakeholders. Here, one of the critical stakeholders is again going to be the designer of the foundation. It is looking back on the topics we had very early on the introduction on your floater. It's about the weight and the control of the weight. Here, the control of the weight for the foundation is going to be critical for the SPMT operation, and also for the stability of the HLV. So you need to know your weight, and you need to know your center of gravity. So when you look at commercial models, you're not going to do weighings and inclining experiments, obviously, for every foundation. But in a demo case, typically, you would expect to have a weighing done. So that's an arrangement of a weighing cell, for example, below a module. You would expect a weighing and an inclining experiment to be done on the foundation. Except that in your case, you won't be able to conduct this inclining experiment, because you will be loading out directly. So you will do indirect measurements with the weighing. Then, in terms of loadings, you need to make sure that the foundation itself is designed to interface with the SPMT. So the SPMT, they are a very stiff structure, and they will distribute the load through their hydraulics on the wheel side. But the contact area between your foundation and the SPMT, you will have an interface structure that has to be designed. It can either be designed by the SPMT manufacturer or by the foundation designer. The reason why you want this interface structure is because you don't want to reinforce the foundation with permanent steel when it is only required actually for the loadout operation. So they will use usually spreader mats or some bridge interface structure between the two to distribute the load from your strong points. So if you have, for example, bulkheads or bigger frames within the foundation down to the SPMT. Then what we need to check when on the design side is going to be the motions and the reaction force of your foundation. Of your foundation when you're doing the transportation. So the transportation, even if it is a short one, you will be subject to the vessel motions, and you will have a new supporting condition. So your foundation started to be built in a static case supported by the assembly facility supports. Then you have an interface structure with the SPMTs, and the SPMT, they will pick up the load where the construction supports are not, because you cannot insert your SPMTs if there is a clash. And then you also need to make sure that the interface with the barge, between the barge and the foundation, which we will see after is the grillage, also will require your foundation to be verified. So it is in 3 different steps. You will have 3 different locations where your foundation can have a local strength impact. So you need to check all these cases. And in this case, they have different range of loads, and they also have different configuration in terms of distribution under your vessel. When looking at the sets of motions to be used for the transportation, there are 2 choices. Either you go for a fit-for-purpose motion analysis using software like Moses, for example, where you will do your free-floating analysis and you put with your cargo on top. Or you can use the DNV table and DNV criteria. That's not the table I wanted to make. That's the table I wanted to show you this morning. But you can use DNV criteria to guide yourself in the range of motion, so maximum roll angles and motion, and that you want to subject your calculations to, knowing that what this table is showing is what I was mentioning this morning. The operation reference period will impact the return period of events that you need to take for wind, wave, and current case. So this morning we are mentioning, for example, if you have 3 to 7 days of operational reference period, so keeping in mind that it includes your actual operation time, plus the contingency time, plus the time from the last weather forecast to the start of your operation. So if you have 3 to 7 days, basically we are talking about 10-year return periods for the wind, 1-year return period for the wave and current. So again, the approach from DNV is conservative. So you need to measure the impact in terms of reinforcement to your foundation or the design of the grillage that can result from it. Then, if the impact is too severe, then dedicated and specific motion analysis for your towing condition and transportation condition might be the way to go. So when I was referring to the interface structure between your foundation and the barge, so this is a semi-sub barge. These are grillage items, so it was not a floating foundation, it was a module that was being transported, so that's the model of this. You need to basically make the connection between your cargo that's going to be on top and bring your loads down to the main structure of the vessel. So you will target the bulkheads, you will target the main frames, the column locations in your vessel structure. The idea, as I said before, is that you prefer to add a grillage interface that is welded to the deck rather than reinforcing your vessel under deck or reinforcing your foundation. So you try to distribute and have a proper load path from your foundation down to the vessel structure. One of the complexity when doing a roll-on with the vessel, with SPMTs, is that you see the way the grillage are being arranged is because all these paths in the middle here, they are all sufficient to provide sufficient clearance for the SPMTs to pass through. So that's something that needs to be kept in mind, is that on top of trying to align with the structure of the vessel, you also need to give enough clearance for your SPMTs to pass through. So in this case, for example, where we needed large brackets that were encroaching on the space, basically the brackets that were installed after the SPMTs traveled through. The next one to check on to prepare for on the design side is that, I mean, it's the point that we made already on ballast on the previous one. So all your conditions of ballast, draft, stability considerations, they have to be done for every step of the float-off operation. So that means having the good understanding of how are you going to launch your foundation. Are you going to launch your foundation with some ballast already in the foundation, maybe partial, but then it means that the loads you will subject either the SPMTs or at least the grillage are going to be greater, because basically you're carrying ballast water in your foundation and transferring this load into the vessel. So then the load is not just your weight, it's not just the 4,000 ton you were talking about, it's the 4,000 ton plus whatever ballast you're putting inside. The other option is you're transporting the foundation without any ballast. But then you have an excess of buoyancy from your, I mean, I haven't seen your calculations on this, but basically the free floating condition of your foundation without any ballast is providing you a very, very, very shallow draft, because you have all your pontoon volumes plus the column volumes that bring buoyancy, and you're only supporting 4,000 ton when you have a displacement target that can go up to 20,000 ton plus. So it's going to be a very shallow draft, and that means that the behavior of your floater is going to be quite different. So that means you can get to an understanding of doing step-by-step float-off, where you will combine the sinking of the HLV vessel with the ballasting, the progressive ballasting of your foundation. But doing that will increase the requirement of submersion of the vessel, of the HLV, because basically you're closing your draft is getting greater and greater. So it's going to be all about finding the right compromise between what is a proper ballast configuration of your floater for your floater to be free floating and in station keeping, versus how much load do you want to put in the grillage and in the vessel. So again, we are back at one of basically it's the commonalities between the three topics that we had today. It's about understanding how the ballast is going to be managed and how it's going to impact your design assumptions. We still continue. There's a lot of preparation for the foundation designer. Next point for the foundation designer, we cannot neglect the fact that you will have a lot of towing activity, station keeping. You will have maybe some mooring activities if you have some temporary stage where you're moored, and all this basically will need outfittings on your structure. So all this secondary steel, you will need, like, for example, pushing bar. So here, like the top part here, like there are bars to push the structure. So all this secondary steel basically needs to be taken into consideration in your design. Not only because it will impact your weight, but also because it's going to drive the operability and how you're going to control the position, what kind of asset you can use, what kind of towing rigging or station keeping rigging you can use. And so all this, they will need to be set and discussed with the offshore contractor. And then you always have the possibility, so some case you have direct push on the structure from the tugs. In this event, it means that you need to have a push area that has been calculated and that has been designed for the foundation. But even if you don't intend for intentional push on the foundation and having a push area, you will still need to subject your foundation to impact loads and verification basically of the vessel impact loads, especially around the boat landings. So you will have requirements for either operational push or accidental push and impact study to do. Again, that will impact your primary steel. and the design of the foundation. Last smaller points on the preparation for the operation with the designer of the foundation. It's about accessibility. We need not to forget that whatever your ballast condition is, which is not your operation ballast condition, because your operation ballast condition will be a ballast condition where you have the turbine, you have your ballast at the level where you target it. So your draft will be your operational draft. But when doing installation and float off, you still need to provide access for the people, while the draft might be different by a few meters from your design condition, from your operating condition. So that means that you will have boat landings that are bigger. You will need access and walkways to access all area of the floater. So typically, that's the wind float pin turbine example. Is that yes, you have a boat landing here, but then you need walkways to access the other columns. Because you need to handle the towing fittings, you need to handle your towing lines from the deck. So obviously, it's not just about safety; it's also about the ability to conduct the operation efficiently. So all these small systems, all these small outfittings, basically, they need to be thought about. Next, on the preparation of the assembly facility. So usually the assembly facility, they will be the ones taking the coordination for the SPMT transportation down to the loadouts. Usually the transfer of responsibility between the assembly facility and the HLV contractor will be at the completion of the grillage and sea fastening of the cargo on the deck. So that's usually where you will transfer the responsibility. And after, the yard is only there for support, for the quayside mooring, this kind of things. But similarly to the earlier points, when you're responsible for the operation and for the loadout, so the assembly facilities will need to define the teams, the coordination, the responsibilities between the teams, the methodologies that are going to be used for the loadouts. They will need to bridge the procedures. So here they have more parties to bridge, basically. They will have to bridge the SPMT contractor, the vessel operator, but also the foundation designer to make sure that they are all aligned and produce a comprehensive loadout procedure. They will need to align the schedules and either issue or obtain the relevant permits and clearances to operate. And last, let's say, more generic plans on the management of change, the tax plans, and the as-it-as ops. So that they will cover basically down to the securing of the foundation on the floater. In addition to that, it's the point I was making before. They will need to make sure that the way they have assembled the foundation is compatible with the loadout methodology. So it means that the way they will do their assembly, and that can be months, if not a year, before the loadout operation, before you even know your loadout plan, you need to have a supporting philosophy and support that allows you an SPMT loadout. So again, it's about early engagement with, for example, SPMT contractors, where they can give you the target SPMT module size and how they would ideally arrange it to transport the foundation. Then the assembly facility shall also make sure that the ground level is fairly consistent across the routes. SPMTs, basically, they can take some elevation variations and they can adapt to it. But they give as a target to basically have a route that stays within plus or minus 150 millimeter elevation difference. And then, obviously, the route needs to be cleared from obstructions and other projects. Another point that the assembly facility we need to check, we saw earlier that we were talking about the verification of the general ground bearing capacity. One area that can be neglected and can be critical for a loadout is the actual wharf capacity. So basically your quayside capacity, especially because you will hold a concentrated load that will come, I mean, a linear load, that will come from the ramp connection to the quayside. That means that you will concentrate, let's say if you're in this configuration, you will have already some of the load on the barge, but out of all the axles, so 40 tons per axle that are on the ramp, half of it basically is being supported on this single location on the ramp. And that means that the distance for the ramp from the tip of the quayside and the capacity at this location needs to be very well understood. So facilities that have that are used to do skiddings, that are used to do SPMT loadouts, they will know and they will have a wharf, and usually it's one special location on their wharf that is designed to accommodate this, because they need additional anchorings of the retaining walls, for example, to maintain and to hold this capacity. Marshalling facilities that are not designed originally for loadouts, they might face some issues here, and so I mean, they can make out with like some extra spreader bars or getting the load to go a lot further. Like Mamwet, for example, they provide some matching supports and matching structures that are used to offset the load and create basically a bearing load on a much broader area. But that's obviously coming at a cost and a complication. Then for the assembly facility, we talked about the mooring bits. The one thing that is going to be necessary is that these mooring bits, they need to be rated, they need to be load tested. So all this needs to be prepared. And obviously the rating of this bollard needs to be in line with the mooring analysis that you will do after. Then some more generic points, they need to provide proper access. So that's a gangway, for example, to go to the semi-sub barge. They need to provide all the services to conduct the wharf. And they need to provide protections and all the clearances for the operation. Then looking at the SPMT. So the SPMT, it's modularized transporter. It is basically based on a unit of 4, 6, or 8 axles. I'll show you on the slide after. And you can combine these units as groups or trains to carry as much load as you need. And these units, they are connected hydraulically, and that helps basically spreading the load down to the ground. So you will take the load from your cargo, and you will have an equal distribution of pressure from your wheels to the ground. These SPMTs, they can maneuver basically very well. They can turn on themselves. I'm sure you have seen some pictures. And so they allow for a very accurate operation and a good maneuvering, for example, to go and position the cargo on top of the grillage with good accuracy. And obviously, it is scalable, so that gives you quite good range in terms of loading and total lifting capacity. The lifting capacities for each train, basically, each step. So if you have a 4-line, 5 or 6 line, it will vary. But we can see that, for example, the capacity for one 6-line, 6-axle trailer is 240 tons. So it is, because it is scalable, having a large number of load loadout trailers below your foundation, it's fairly easy to scale to get the target load that you need. So there are a lot of brands and a lot of people operating these SPMTs. The famous brands, they are like Mamwet, Sarens, Boxeng, and China Heavy Lift, Alpha Jolie. They all have a range of SPMTs. They don't necessarily have their own brands of it. The famous ones like the Kamag and Shoulder ones. But the fleet of these SPMTs is quite broad, and they can be brought from, let's say, either civil work locations where they would use the same thing, from oil and gas locations, they would use the same, and so it is a resource that's easy to supply. So in the case of the floater, for example, if we were to use an axle distribution and having a 3-point triangular stability support, we would use 48 axles in this case. So you have double trains basically that are mounted side by side. And how you're going to get the sizing and the selection of the number of SPMTs is, yes, going to be the footprint and how much you want to distribute the load from the foundation. But it's also based on the input in terms of your total cargo weight and contingencies with the interface structure weight, so anything that you need to add to your foundation or your SPMTs to take the load, the sea fastening. So it's a bit, it's not the same scale of sea fastening as what you have when you go at sea, but ultimately, when you're doing your SPMT transportation, the SPMT and the cargo, they are lashed together. So they use turnbuckles, they use lashings, they will weld some pallets, but basically they will need to be able to take the loads, especially coming from acceleration and braking. So it's usually more braking than acceleration. That can happen when they do the transportation. Then they need to cope with a maximum slope. So the maximum slope is actually governed by, I mean, DNV will give you, for example, a criteria for a minimum slope to be used, but else you need to use the as-built of the site, and obviously the wind, depending on of your structure and the windage area, it will create large lateral loads on your cargo, and that will affect the distribution of the loads on the SPMT. So once you have all these loads, what you will check on the SPMTs is the maximum load per axle. So what we saw on the data sheets, for example, is that whatever the number of trains for the Scholler model, it was 40 tons per axle. So the 40 tons per axle is what gives you your 10 to 14 tons per square meter. But you will also need to verify the maximum bending of your SPMTs. So typically, if I wind back, what's going to happen is that the top and bottom trains here, they have a fairly consistent load transfer from the foundation to the train here. So it is releasing a lot in terms just of vertical loading and very limited bending. However, when you look at these trains, for example, on the aft side, you will have a significant bending of the SPMT spine here, and this needs to remain within an allowable value that is defined in the SPMT datasheet. And that's why usually this kind of arrangement, so one extra train might be okay, but usually they will need to add an interface structure between the last SPMT trailer, and the foundation. So they will use like a very stiff mat, for example, and that will add to your interface structure between the SPMT and the cargo. So you need to meet your maximum bending moment, and then it is about stability. So because there are hydraulic systems, basically they will look at the maximum inclinations that's going to be reached during the operation. So you have one where you consider just the root, one where you consider the root and the impact of the wind, and the fact that the wind will shift the distribution of the load. And as I was saying, you also have a minimum inclination to be taken by and to meet from DNV, for example. At the bottom, what's illustrated is 3 groups, and that's the stability triangle that the SPMTs are going to work. So the way it works is the group, let's start with group B, for example. So the group B, so the center of gravity is here, it's the point in the middle. Your group B will bring some of the SPMTs that are at the aft of this location. So all this, they will be linked hydraulically, which means that they will share the same load and they will distribute the load within this SPMT. Same goes for the group C. The group C will provide a global reaction force on the triangle with all the trailers of this group. And then group A is actually going to be linking the hydraulics of the forward trailers on the upper part and on the lower part. So basically you will have one global reaction force here, one global reaction force here, and one going here. And that's how you provide the stability triangle and how the SPMT calculations are being run. So we were mentioning the interface structure. So obviously you want to minimize the reinforcements. So you will try to spread your load. In this case, it's a fairly straightforward pancake module structure, so it goes nicely. But this interface structure, they can be fairly complex. Typically, when you're working with a foundation that has it's a triangular shape like this, I'll take your example. If you were not able to have this configuration, and you had to put, for example, one trailer here in the middle, a train of trailers here, and the 2 sets, you put them at the aft. That would mean that your support structure would actually be a superstructure that brings the load of the SPMT to the foundation via a large transverse structure. I think there is a picture of the PGL1 where we can see what they had done. But basically, that's the minimum you would have. The maximum would be a much broader, much wider structure to basically catch the foundation points that you want to support from. Then next point on the SPMT side for preparation is the ramp. So as I was saying here, we're not talking about the ground part, but the ramp itself. So obviously, the ramps usually are being welded on the barge side. So you will have a slope that is welded, and you will have a hinge connection here, so that your ramp can move together with the heave of the vessel and the tide. The ramp is only being deployed when you're doing the actual loadout operation, else the means of access are different because when you're waiting and preparing, you don't want the ramp in position. You want to be able to go for low tide, typically, without having the ramp in the way. So the ramp usually would be parked to allow the vessel to go up and down. And only when your operation is in a readiness state, then you install your ramp and you start the ballasting control that we'll see after of the HLV. So it's just some of these ramps, they exist on catalogs. You can rent them, and basically the SPMT providers, they will come usually with their own ramps with the SPMT. And last points of preparation for the SPMT is gaining the understanding of how the cargo is going to be moved from its fabrication or assembly location down to the position where it will be inserted onto the transportation vessel. So here, it is fairly straightforward. It's basically just a move forward to get away from the construction supports. So one move forward to get away, then kind of a crab translation, diagonal translation, to face the ramp and go on board. But you also need to consider that you have an environment around. That was like another construction project that was just beside. So you have limitations, and the knowledge of the site is important to plan the operation and getting the timing plan right. That's for the SPMT. Any question on the SPMT preparation? Can I take some copy? Okay, I'll continue. So HLV. So as we said earlier, the transfer of responsibility would usually be done at the completion of the loadout of the foundation on the grillage once the sea fastening is complete. So basically, the shipyard will perform the sea fastening activity once the NDTs are finished on the sea fastening. Then the handover goes to, the handover is done to the HLV. The main responsibility, I'll go quickly through this, but it's always the same thing. It's about once you get the responsibility for the operation, you are responsible for setting up the team, clarifying the roles and responsibility, making sure that the methodologies and assets are in line with the intended operation, that there is a good understanding of the schedule and that is being shared, and always the same. Managing your operational envelope and the weather window strategy, and the general plans for as-built, as-op, task plans, and management objectives. Again, all this, even if they sound repetitive, but they will have to be produced. Every stakeholder who holds this responsibility, they will have to do their own set of documentation. They will have to produce all that. There isn't going to be a single person on the project that's going to produce all this. It's different parties, and it depends on the contracting strategy. It depends of who is holding the responsibilities at the time of operation. But that's critical for it to be aligned as early as possible.
Just something that as well as we see this sharing of contractual responsibility. So that part I think need to pay a bit more attention, especially if you start constructing, for example, Vietnam, bringing back to TIC, going for HLV transport. Who is going to take what responsibility at which point in time? The way to do this project management is something that is very, very important.
Yeah. I mean, basically there should be no gray area in terms of responsibility. And that's where it's complicated, because when you lack the experience, obviously it's you try to rely more on subcontractors and on people who have done it. But that's why you get some gray area that are not being flagged out. So the first activity and the first check for the HLV is on the mooring side. So as we said, and it's back to the table of operation reference period. How long you intend to stay restricted to the quayside is what's going to drive the selection of your return environment, your environment return period. As we said, you can base it, that's based on the DNV STN1. Yeah, there are, you can do site-specific calculations, but ultimately, even if you do seasonal calculation or monthly calculations to cover your operation window, the return period, even if it's on a monthly base, will still need to be 10 years or 1 year in this event. In all likelihood, your period of time where you're going to be restricted at the quayside will be either 3 to 7 days or up to 7 days. When you have a pretty straightforward operation, basically you consider that your mooring is restricted as soon as you start your loadout operation. Before that, you can have a safe mooring. You don't have cargo on top of your HLV. So, which means that your HLV, the mooring loads that the HLV is going to see are much lower. for example, if you're doing a stern offloading with the HLV, you can get back to a alongside configuration and have a very safe mooring on your quayside. Or you can sail away and go to a shelter if you need. So that's why when you start your loadouts, basically your SPMTs and the cargo is ready at the quayside, you drop your weather window is here, you drop the ramp, then you start the clock. And the clock will end once your cargo is sea fastened securely to the grillage. So you need enough time to bring the cargo in position, so cross over on the vessel, land on the grillage, secure with the sea fastening, and that includes also any period of visual inspection and NDTs on the sea fastening to consider the operation as complete. So when you have only one cargo, which is fairly straightforward, that is achievable in the 3 to 7 days period. But if you were to have more than 7 days, then obviously the environment that you will need to consider would be different. So mooring analysis, for example, that's an example of a mooring analysis run for the loadout I was showing on the previous slides of the module on it's a stern loading on a semi-stud vessel, on a semi-stud barge, sorry. That's the one I was showing you this morning, the weather forecast. Basically, this direction is highly subjected to squalls and high winds value. It's very exposed. It's on the west end of Singapore. And we had no choice because of the quayside and the fact that there was another project here. We had no choice but to do a loading by the stern of the module. But this configuration is very demanding for your mooring lines, for your bollards on the quayside, and for your connections on the barge side. So you will need to consider your intact condition with all the wind, wave, and current effect that will apply on the vessel and the cargo. That will be subject, obviously, to the variations of draft that you can have. And one of the biggest contributor to the variation of your mooring lines, at least the pretension in it, is going to be the tide effect. The variation of tides, when you're not doing the actual loadouts, when you're just moored to the quayside, the tide is going to get your tension to vary on the mooring line. So you can have different ways. Some will accept to have lines that are just installed in a static way, and they accept that there are variations of tension. Else, some of these mooring lines can be connected to a quayside winch, so that you can control the pretension in your mooring line and prepare in case of, let's say, if you have a more severe weather forecast, for example, then you can prepare your mooring lines, take more pretension in it. And this mooring configuration will also need to be checked in the event, what they call redundancy check. So it's the event of one line breaking or not being effective anymore. And then you need to check that in the worst directions, despite any of these lines being broken, you still meet your mooring line and bollards and fenders, compressive port also, but your bollards force. As we said earlier, you have a rating on this. You will have a rating on your mooring line. You will have a rating on your mooring bits on the barge itself. All these are subject to some safety factors, and you have to comply at any time with this arrangement. Having in mind that this Optimo is like a quasi-static mooring analysis solution, so it's basically looking for equilibrium in the system. When you have complex mooring locations or let's say a bit of an awkward solution, in the same way as you can do time domain analysis for Moses, for example, when you're offshore, you can also do dynamic analysis on the mooring. The quasi-static is a good first approach. But when you start to have more complex, and especially when you start to have, well, in this case, it won't really happen, but when you start to have tandem vessels that are moored to another vessel that is moored to the quayside, and that you have basically the behavior of two floating objects on the mooring, then you have limits with this methodology, and you will need to use a dynamic approach.
I think to add on to that, there's also something to be careful about. But it is in this kind of mooring configuration, the lines are all heavy. So the tension is largely EA over L. So based on the stiffness of your mooring line. But EA over L is not linear. I mean, the calculation is, the formula is linear. When the line is stretched to a certain extent, it becomes that you either break, actually the E will start to, so your A will start to deform. So it becomes nonlinear in that extent. So just be careful that if you just use, let's say, frequency domain analysis to run this, if you exaggerate too much, something is actually wrong with your analysis.
Thanks. So yeah, so the limitations, as we said, it's not only your mooring lines, it's also anything that your mooring lines are connected to. So it can be bollards, can be you will have limitations with respect to the capacity of your fenders. So between the quayside and your vessel, you will have fenders that are working in compression. They have limits, they have maximum capacity. So all this needs to be satisfied. Then after mooring, obviously one of the main topic on the HLV is going to be stability. And there again, the stability is not just a one-off load case like what you have for transport. So transport is one configuration. The loadout is going to be, and you will see after, is going to be a step-by-step loadout approach. So your stability, your longitudinal strength will have to be checked for all these steps. Same goes for the float of operation. As we said, the float of operation will see different ballast configuration on the HLV, but maybe also different ballast conditions on the foundation itself. So it is a large number of stability configurations and 10 configurations that is actually going to be run to check a loadout, transport, and float of operation. So yeah, that's what I mentioned here. That's just an example, for example, of one. So using GHS as the stability software. So it's one tank configuration, which is an awkward one because these tanks were being repaired. But that was one step to meet the loadout condition for the modules. And I try to keep the same examples through the presentation. So it's still the semi-sub vessel and the module I was showing you before. So obviously what you are targeting at is to get below your permissible shear and permissible bending moment. And meet your stability criteria, obviously. But it's not only your global stability and let's say the longitudinal strength, the global longitudinal strength that you need to look at. As we started to when we mentioned about the grillage and the impact that the grillage can have on the foundation, obviously the grillage has an impact on the vessel. What we said earlier is that we want to make sure that this grillage here doesn't impact the reinforcement below your vessel, but I mean, you can wish for it. You will need to verify it also. So that means you don't always have to necessarily model the full vessel structure. You can focus on some local area. But basically, you will need to get an understanding on how your underdeck is working and how are you utilizing your vessel. Having in mind that your grillage, you're free to put the thickness you want. You're free to put the material grade you want. Your foundation, usually, you will have high strength steel. You will have a range of thicknesses that are, let's say, on the higher side. These barges, I mean, they are usually, I mean, they are vessels. They are pin plated, and they can be very sensitive to loading from the grillage. It's not only the loading of the sea fastening and the grillage. So the sea fastening and the grillage basically transfers your load from the foundation to the glue structures into the vessel. It's also the SPMT axle load. So as you're traveling, well, this one is as a deformed behavior, it's a transportation model, but as you're traveling, let's say you're loading your SPMTs from here, you are still applying 14 tons per square meter on the vessel structure all along the pathway of the SPMT. So knowing if you have limitations in terms of your barge deck local strength, because you cannot take this 14 tons per square meter, and then you need to specify maybe more SPMT trailers to be installed, is something that you will need to consider early. And last, you will have some float-off guides that are usually welded to the decks when you do a float-off operation. Again, they are not very impressive structure. It's usually just masked with bracings, but they will have impact on your. They will have an impact on your vessel structure, and they will need to be checked. So now, the core of the management of a load-out and float-off operation is ballasting. So when we are doing a step-by-step load-out, you can see that you want to progressively load, let's say, axle by axle, so one set of wheel by one set of wheel, onto the ram, and then onto the barge. So slowly, your cargo, you can control the speed at which you transfer the load from the quayside to your barge. If you do that without adjustment of the ballast, basically, your barge will just go deeper and deeper into the water to a point where the ramp will touch the quayside, to a point where it doesn't work anymore. You will break something, the ramp or the SPMT. So you will need to manage your ballast first to compensate for the load transfer that comes from the SPMT going from the quayside to the vessel. So in theory, you have your SPMT weights, you have the cargo weight, you know that you need to transfer 4,500 or 5,000 tons of ballast, in theory, if that was also so simple, to compensate for bringing this load onto the vessel. But in the same time, taking the example of Taiwan is a good one. So I took the Hinshu buoy tide data for February. Some days, your maximum tidal range, so the extreme between your highest tide and your lowest tide, is a meter. So that's very straightforward. You have 6 hours to go through a meter of tide variation. It's not. I mean, it's not a lot. But then you will have a few days later, weeks with more than 4.4 meter tide variation, still within the same 6 hours. And the tide velocity is not linear. I mean, you've all seen how a tide chart looks like. Basically, you plateau a bit on the high tide. Here, it's because you have many days, but you plateau a bit on the high tide. Then you have a fast tide receding or coming, and then you have a small plateau at the low tide. So, choosing the date of your operation will have an impact on your ability to, and your understanding of the ballast operation. You can aim and tell yourself, okay, I'm only going to do the operation when I have very low tide. But if you do that, and in practice, you end up here, you will have insufficient ballasting capacity, or your ballasting plans, they won't be aligned. So usually what you do is that at the start of a project, you take a conservative assumption on where your marshalling location is going to be. You take not the greatest tide variation, you try to remove like the highest astronomical one and let's say the extraordinary events, you try to remove them. But then you look at your maximum tidal variation and you check that your barge can ballast and transfer sufficient volume to be able to do in the same time the loading and the load transfer of the trailers of the SPMTs onto the barge, in the same time compensate for the tide that is arriving. So a crossover, the picture that you saw before with the modules, the crossover time from the SPMT putting the first wheel on the ramp to the load being fully on the vessel was around an hour 20, an hour 30. SPMTs are not going very, very fast, but that's the speed more or less that we are looking at in terms of window of operation. So that means that during this hour and a half, your tide would have changed, and the impact in terms of ballast transfer from the tide is actually more important than the actual load of the cargo. Meaning, if you have a meter tide variation or even half a meter tide variation in an hour to compensate for, that will drive your ballasting calculation and your ability to transfer and pump in or pump out in greater quantities than the cargo itself. When you're doing the actual operation, what you will target is basically for the ramp to maintain its position, its relative position to the quayside. So you will prepare a few days or a week before the operation, when you know the dates and you know the time. So usually we will try to go for a rising tide event, meaning we start the operation let's say an hour, less than an hour after the lowest tide, so that we get to a case where if we become late and we don't meet the ballasting speed, the worst that can happen is that there is more separation between the quayside and the ramp. The opposite case, if you do it during a tide that is lowering, the risk is that if you can't meet the deballasting speed, is the case I was giving you, is that the ramp will actually clash with the quayside, and you will end up supporting the SPMTs with the ramp and break the hinge of the ramp. And that's catastrophic. So you always try to target a rising tide event. So it's good. There are 2 every day. So sometimes you wake up early, but that's what happens. And you will monitor your ballasting as good as the plan that you have. The loadout master will have someone looking at the ramp. He will have a little ruler, and they will measure, for example, 10 centimeters from the quayside to the ramp when the ramp is crossing at the edge of the quayside. And for every variation of a few centimeters, they will instruct the master of the barge to ballast or to deballast to make sure that they maintain this. So it's actually a very practical approach where they don't necessarily go into the details of the procedures. The procedures are here to show that you have sufficient capacity to do it. It's not going to tell you exactly how you're going to do it, because you don't control the exact speed of the SPMTs with regards to the timing of your operation and the tides. So it's about live monitoring of the operation and having people who have the experience to monitor and run these operations on site. So they will monitor this distance, try to keep it within this 0.1. The SPMT basically will give you a maximum value. This maximum value is driven by the maximum slope calculation that we had calculated before. So it's how much maximum slope you can take. And it can never be close or below 0. Close or below 0 means your ramp is literally touching the quayside at the edge. All these calculations, they will drive you to this kind of table. Blurry, but basically I'll just explain to you how it works. That's basically your step-by-step ballast plan. In horizontally in all the columns, it is step-by-step of times, like every 10 minutes, I think, or every 15 minutes. So because we know the dates of operation, we know the expected tides, we know the elevation of the quayside with respect to the water and all that. So that's our top data. So that's the setup of our operation. It's what are our different elevations, what is the time of operation. And all these are discrete steps, and all this, they cover the hour and a half or the 2 hours that are required for the operation. Then all these lines here, all these rows, they are all the ballast tanks that are available, that are in the vessel. Some of them, like the grade 1, for example, they were out of service, so we couldn't use them. Some of them are some tanks that are not being affected, like all the day tanks and things that are not ballast tanks. But then what you will do is that for every step, you will assess how much volume do I need to transfer from what tank to what tank or outside of the barge, or I need to onboard. So how much variation per tank do I need to do? And what is this variation mean? What does this variation mean in terms of the speed and the requirements of my pumping capacity? So how many cubic meters do I need in my pumps to perform this transfer from step 1 to step 2? So here, for example, in step 1, the orange ones are the tanks that basically we are changing from previous step. So from step 1 to step 2, we change the configuration of 4 tanks. Then to third step, we only change the configuration on 2 tanks. We add some water there. Then we change another one. And the selection of the tank is basically, we need to distribute the overall vessel draft to have a keel level that remains as level as possible. We are not trying to create, basically, as we are loading cargo from the side or from the stern, we are trying to maintain our keel level. So that means transferring, if we do, for example, alongside offloading, that means transferring some ballast from the quay side to the outboard side as we transfer. And the outcome of all this sequence is basically, what is our maximum ballast speed that we need? Do we need to ask the SPMT contractor, for example, to operate slower or faster? Faster, usually not, but usually slower, because it gives, operating slower gives time for the ballast to catch up in terms of transfer of volume. And then after, you will have some calculations, because obviously you cannot operate with just what's enough. You will need to operate sometimes with external pumps that act as redundancy. Sometimes just you need to demonstrate that you have sufficient spare capacity in your system. And that will give you basically the result at the end is what is my draft, what is my vessel condition in terms of roll angle and pitch angle. So that's a broad picture of what do we try to achieve when we do a load-out plan and how the ballast sequence actually works to meet the operation. So that was for the load-out. For transportation, it's actually very straightforward. It's a single case, and it's usually a case where we try to select our ballast configuration to minimize motions. In your event, you will see how much load is being transferred from the cargo to the vessel under motion. You have a short transfer. You expect to have a short transportation and weather controlled transportation. So you might need a very limited adjustment at departure, but basically the idea is, okay, I want my transport condition once I leave the quay. For the float off, I'm not going to present it again, but basically you need to do the same work in terms of ballast sequence, but this time your limiting criteria and your variation is not your quayside elevation, is not how much clearance do I have with my run, is how much clearance am I creating with my foundation, knowing that your foundation is also sinking, gaining drafts up to a certain point, and as we said, will be impacted also if you're ballasting the foundation in the same time. So that's why understanding the launching condition of your foundation is going to be important to understand if you want to launch it with partial ballast, with anything, or But the principle will remain exactly the same. You will want to verify that your HLV has sufficient ballast capacity to reach submersion, gain clearance with the foundation. The chance is that you have transportation vessels that can do SPMT loadouts, and they are not necessarily semi-sub vessels. They can be just for dry transportation. These vessels, they will not have an as good pumping capacity as a semi-sub vessel, because you can imagine that a semi-sub vessel, to get it to this condition, you need very high volume and very high output of your pumping system. So when you are looking at semi-sub assets, it is very rare that the pumping capacity is going to be a limit for you. It's quite rare. During the float off, the operation basically and your target, it's to gain separation of your floater so that your floater is free floating, under control by the tugs, and sometimes you can also have some tieback lanes that connect to the HLV vessel. But the idea is to understand what draft do I need to reach with my HLV to get the floater into the free floating condition, and where can I do this float off location to have sufficient clearance or sufficient water depth to do the operation. You have two philosophies. Some HLVs are compatible with bottom approach, which is basically they can accept to have the aft bottom of the barge to touch the floor, to touch the seabed. This way, I mean, what they say when they do that is basically, in terms of position control, they favor this approach when they need to stay in this position for longer durations. But else, the majority of HLVs, when running more, let's say, faster operations and with benign environments, they will remain in an even keel situation, configuration, and just gaining even clearance between your bridge supports and the foundation. So here, when we take the example, I took the White Marlin as an example. So the vessel depth is 13 meters. The bridge, I took a couple of meters as an assumption. The foundation draft at loadout in this condition is basically the estimation of your floater without any ballast inside. It's a very, very small draft. So that's why you might want to consider what are you doing with that. Then you need to create sufficient clearance between the bridge and the foundation so that the free-floating heave motion of your floater and the variation of motions of your HLV are not going to create a clash and a collision here. You also need to create sufficient clearance so that your AHT can pass over, depending on how you operate it. But basically, if you have buoyancy towers that you have done alongside key type of loading, you will not be able to exit from the stern of the vessel, of the HLV. You will need to exit from the side. In this case, you might need an HLV to actually pass atop not the HLV, the AHT to pass atop the HLV. So you need to have sufficient clearance. And then for the ones who wants to operate without having contact with the seabed, you need a seabed clearance, a quick clearance, and that can be a couple of meters. So for launching your floater with a very, very small draft, you actually already need 25-meter water depth and a deck submersion of 10 meters. So the deeper you will go in draft, the deeper you will have to go in terms of deck submersion and water depth. So that's why this type of operation, you won't be able to do it easily in a harbor condition or in a very like a nearshore sheltered area. You will have to do them in location where there is sufficient water depth, and that means being exposed to more of the wind, wave, and the current conditions. Last reminder on the weather forecasting, because it is as critical for this float-off operation as for the previous ones. So again, as a reminder, while we might estimate a time of operation for the float off that would be in the range of a few hours, the ability to have it done in the weather window will depend on when are we receiving the last forecast, what is our contingency period, and so that will define basically our operation reference period. The float off operation usually will go down to the DNV criteria that are below 3 days, obviously, even with the contingency. Because when you start your float off, there is no turning back. So the operation goes forward, and there is no intermediate step where you can stop. It's not like the loadout. The last preparation steps for, the last two, sorry. One is offshore vessel. That's very straightforward. Basically, as you're going to prepare for the float off, you will need to connect towing lines or station keeping lines from your foundation to the spread of AHTs or tugs if you're operating near ports. So the idea is that they will be here in position. They won't carry any load until the foundation actually starts to separate from the HLV. And once there is sufficient clearance between the two, they can gain full control. So they can gain full control of the foundation. The in-between stage, when you cannot have full control with your AHT, but you start to have separation, you try to keep this timing to the minimum because you don't want the heavy impact of the bottom of your structure. You have to look at it anyway, but of the bottom of the structure on the foundations, on the grillage. But you will maintain position thanks to the guiding post I was referring to earlier, which basically are going to act as guides to keep your foundation in position until it is free floating. These guiding posts don't need to be, it doesn't have to be meters and meters high. It's just about controlling the position of the foundation until you can gain control of it with your AHT. So the AHTs there, they have nothing specific to be required as long as they have sufficient bollard pull to keep control in the weather conditions. They will be the spread basically that you would have defined for your hookup procedure. So for your hookup procedure, you need to define a station keeping spread that is compatible with the duration of your hookup. That's the spread you're going to use here. It's not going to be driven by the float. It's going to be driven by the duration of the hookup.
Can I go back to the slides? Yeah, so here I think it's something similar to what we did just a few years ago on float over. So the other, it's opposite essentially. And the guiding post that JB was mentioning is somewhat similar to the LMU and TSUs, where there's initial separations, there could be movement of the floater, whether you need a guiding post or you need a polymer to soften those loads, something you need to design and analyze in steps.
No problem. And the last one, the MWS, again, same. It will depend on your stakeholders' requirements, but these are activities that are even more relevant in terms of marine warranty survey, especially loadouts and float off. But basically, the range of services would bring you the inspection, would bring you the document review, the coordination of, can help with the coordination of operation on site and the witnessing of all this. Now going to the actual execution of the operation. So as we said, we have the HLV that will come in position, that will be moored. In this event, we put it alongside with the key. Well, it's positioned in here. I mean, we saw it on the first picture, but you have your fenders, you have your mooring lines. In this case, the ramp is already shown here. You will present the foundation with its SPMTs So the idea is you jack up your foundation, you bring your foundation near the loadout location, then you're still in a safe position. Basically, you can keep your foundation holding on the SPMTs. The SPMTs, they can be locked hydraulically, and you can even choose to stroke and jack down your SPMTs to the minimum in case you need to wait. As long as your foundation is able to take the load from the interface structure under wind conditions, you can basically just wait for your loadout window to open with the foundation and SPMTs ready just in front of the ramp. Once you have the operational range of the SPMT, so when it's about just land transport, the SPMTs that are in their data sheets and depending on the cargo, but you can operate up to around 15 meters per second wind, and that's the one that has the most impact on the foundation. And you will bring it basically. You'll bring it from the construction support to the site. You will have to lash do the sea fastening basically of your SPMTs onto your foundation, and you can be ready for the loadout location. So keep a few meters. When only then you will be monitoring your window of operation. So you will get your go no go in terms of weather forecast with regards to the wind acting on the foundation and the SPMTs, but also the conditions that go around the HLV, the mooring, the motion, and so on. Once you're ready, you will lower down the ramps, put them in position, and you will start your ballast management. So you will start with your initial condition, and then you will progressively and actively manage your ballast to cope with the transfer of the load and the tide variation during the operation. You will position that's on the next slide. You will position the cargo on top of the grillage. So here the grillage is shown as these three parts here. So here it's on top, so we can see we took the white marlin, but even with that, we can see that we are supporting only half of the columns to stay within, basically to have the grillage within the breadth of the vessel. So once you are with the SPMTs on the vessel, then there is one extra step of ballasting that you will take, which is to adjust the ballast to your grillage loading condition. The idea is that you want the ballast configuration, the shape of the vessel, to be in line with what you have prepared for the distribution of loads of your grillage. What I mean here is that if during your loadout configuration you have done a lot of ballast, let's say deballasting at the center part of your vessel because you brought your cargo in, and that you are creating a situation where you have a vessel deformation that impacts the transfer of loads from the grillage, from the foundation to the grillage to the vessel, then you will need to compensate for that. And that means transferring some ballast to make the grillage distribute the load as, at least in the static case, we're not talking about the dynamics of the vessel, but at least in a static case where the distribution of your grillage load is as distributed as possible through your foundation. Once you have this ballast configuration, basically you can jack down and slowly transfer the load from the SPMT to the grillage, and you will load the grillage progressively. Once the load is fully transferred to the grillage, you can remove the SPMTs, so you will exit the same way as you came in. You can remove the ramps, and at this stage, you become clear of your tidal variations. So the ballast management doesn't have to be active to compensate for the tide anymore. And you can start your activities in terms of securing the foundation on the grillage. And with the sea fastening. In your case, because again, we are going for a short transportation event, and we have a float-off configuration, we want to avoid sending people before float-off to cut sea fastening and to cut welds and this kind of things. Especially you can't repair your structure after. So the idea will be to do a sea fastening that is mostly done using guides, using stoppers, and have as little cuts to do or mechanical removals to be done before the floater. So that can be done, but that needs to be thought so that you try not to damage the foundation. You don't want to have to cut something that has been welded to the foundation, so your foundation after is going to be in the water. So that's the aim, and the smart, let's say, sea fastening is to limit this welding work. Once the welding is complete for what has to be welded, so usually you will weld on the vessel side or on the grillage side, you will need to wait to be able to conduct your visual inspection and NDTs of the weld. And then you are in the safe condition. You can start preparing for the transportation condition. And at this moment, you will hand over the responsibility from the assembly facility to the HLV operator or contractor. So now the HLV operator is responsible for the cargo and has to basically do the coordination and the procedures for the transportation and floater plane. So the transportation is actually very short. So it's very likely that you will have easy go, no go to have. But what you need to keep in mind is that if for you, your cargo and your vessel is safer being at the quayside in a harbor, and you don't have the operation window to conduct the transportation and the float off, and in some events, you might even want to include even the hookup phase into your window to make sure that you are not going to have to return to port with your HLV, or you will not have to tow back the foundation to port. So if you have weather restrictions, for example, for hookup that are more severe than for the float-off and for the transport, which is usually the case, what you will want to look at is not just your transportation window. It's your hookup window that is maybe 2 days down the line. And that's where the operation window that you will look at is actually going to be much broader than just looking at the activities one by one. It is always manageable if you do a transportation, you do your float off, and ultimately the conditions are not good for your hookup. What's going to happen is that your contingency plan will probably drive you to bring the foundation back to a sheltered location. It means you have your towing spread that is ready. You will bring it back to port. As we said, you are today in an environment where you have a fairly favorable marshalling locations that are in like 40 nautical miles away. It's probably going to take a little longer because you're probably going to have a 2 or 3 knot stow, but you will have sufficient notice to say, okay, I cannot do the hookup. I have time to tow back to a sheltered location, and I will wait. I will wait here. So it's all about when preparing your planning and your weather restrictions selection. Where do you want to put your risk? If you feel that you want a broad window of operation, that will drive some items in your design. You might need more reinforcements, you might need more grillage, you might need, for the hookup case, you might need to be able to take more of the motions of the floater during hookup. or have bigger AHTs to have higher bollard pull. So all this will have consequences. So here, when we look at the go, no go, as I said, we're not only looking at the transportation, we will try to look at the operations until the next, ideally, hookup storm safe case. So we'll sail away. So we'll sail away, and basically the HLV can perform the float-off either on DP or a combination of mooring lines, depending on basically if you have easy access to mooring points, or you can lay your anchors easily. You can use mooring lines to control the position of the HLV, and use your mooring winch basically as you're sinking, as you're doing the floater, to control your position. So next step, when looking at the float-off, as soon as you are initiating the float-off, you need to be connected to your tugs. So at the start, they will pay out the towing line not to transfer any tension, and keep sufficient clearance between the AHT and the HLV. But these lines, they need to be pre-installed. Either, usually it's on the foundation side and they are thrown to the vessel. It means that before the operation starts, you need to have done this transfer. Then, so it's here. Once you're connected, that's where you can have another go no go for your float of operation. Once you have a start, basically you will cut. So as we said, if it's like, for example, a holder with a cut to be done on the bridge side, you will need to cut offshore or disconnect if it's a mechanical connection, for example. In your case, uplift is very unlikely on a very short transportation like this. So you could probably have sufficient lateral guides that basically hold the foundation on the grillage, and make sure that in the extreme roll events that you can have, or the extreme motion events, you don't have any risk of uplift and any risk of a failure of your system. So all this you can calculate, all this you can verify before doing the calculation of your sea fastening. The priority is basically to minimize the sea fastening, so that offshore you have as little work as possible to do. You want to save the time and the people that are exposed to risk, because keep in mind that if you need to cut sea fastening, you're cutting sea fastening under your floater near a side shell. Ideally you try to minimize it. Once the cut and disconnect, so it's obviously it's a point of non-return. Once you're cutting and disconnecting, you need to go through with your floater, and you will start the submersion of the HLV until the foundation is afloat, and the station keeping is done by the guide post or the guides and the tugs. With sufficient clearance, then you will bring the foundation away. So it's usually the foundation that goes away. It's not the HLV that sails away. In this event, because we even have the buoyancy towers, basically the HLV is stuck here. So you will bring the floater away, and then the HLV will start. The HLV basically, before coming back to the surface, you would have moved your foundation away from the HLV. You will bring it to your hookup site. It would be in close proximity, keeping the same, as I was saying, keeping the same tug arrangement to do your station keeping, or to do wet storage in this case, I mean, as we said, if we are not going straight to a hookup phase, but you actually want to bring back the foundation onshore because you want it to be at quayside to run some operation or preparation, it is still possible. You will use the same spread and bring it to shore. And once we are, in this case, it was assuming that you would do the hookup, but basically what matters is once you are clear, once this basically it's its own separate operation, you will look at the HLV, you will resurface, I mean, you bring the HLV back to its normal draft condition by deballasting, and you can demobilize the assets for you to either clean up or recycle or reuse the grillage. So that's where I was when I was telling you, when you're using assets for this kind of operation, you try to use the same assets so that you can share the use of grillage. And this grillage can actually be cut, can be reused. So ideally, you try to make it so that it doesn't go to waste for every float-off that you're doing. And this one was just to illustrate should work. The actual operation should work. Yeah. So that's the one. I don't know if I can put full screen. Yeah. So that's the PGL project I've been mentioning a few times. So, that's not the one. Sorry. I'll press pause there. So basically, I'll probably not play too much with it. So that was a loading. You will see it was a loading that was done from the stern of the vessel. So here the foundations, they are on the SPMTs. The grillage is actually very small, so that's the move with the SPMT. The grillage is just where it was just supported by the central column, and it's a configuration that was quite similar. It's basically very short transportation. So here it's a barge, so it doesn't have its own propulsion system, bringing the foundation away and starting the float-off operation. So you can see that they are creating a little bit of angle for the foundation. It's to help with the exit of the foundation from the stern of the semi-sub barge. So here they are slowly sinking the asset. This image is weird because you'll see it comes back to the vessel after. But basically the idea is you see that now the columns, they are probably around halfway submerged. So your draft is increasing until the buoyancy of the asset is sufficient to free float. And after, I think it's just the blades. And that was the offshore installation. Yeah. So just to illustrate a bit the operation. So that's why I was saying the float off, even for I mean, it did not start with floating wind, but it is something where there is some experience already, and there are specialist contractors that are knowledgeable in all that. So yeah, now if there are some topics or discussions that you were interested in for the loadout and float of steps. Anything you would be interested to either detail a bit more or to have some information on?
In the beginning, we choose the HLV. We will, the one factor is the price of ship. But I saw the video, the foundation is over than the ship. So it's okay for.
It's okay for, I mean, in this case, as we saw in the video, I'm trying to. Can I open it in the. I'll just put it back into the player so we can pause it. I'm not sure. I'm not sharing the good screen. Sorry. So the view that we had here, for example. So this is the grillage. So it's actually quite limited. In this case, because the TLP and in this event, you have a central column, you can support from the center of the foundation. But indeed, the main issues that we had and that we had to work on is that when you look at here and the overhang that you have, if you have a little bit of roll on the barge, very quickly we had a case of these buoyancy tanks touching the water, and basically you start to contribute. First it creates some uplift on the grillage, and then you start to contribute to the stability and the waterplane area of the barge. And we have run some simulations where you have some catastrophic failure. Basically, when you start to have very high amplitudes, what happens is that you dip the buoyancy tanks on one side. It creates a very high restoring force that sends even greater roll motion in the opposite direction, which then sinks the opposite buoy, and you bring it back. And in some events, depending on the frequency of the roll motion, you could end up having a full uplift of the foundation, because here this is a lot of the buoyancy of the TLP. You have a central buoyancy tank, but else the biggest contribution are the contributors are these side buoys. The braces here, they are fairly small in diameter, so they don't contribute much. So this kind of configuration, in the same way as the configuration we have seen before, where you have an overhang of parts of your buoyancy or your columns, it is okay and it is manageable for short transportations, or really when your objective is only to take it from a quayside to a float-off location that is just, you need to go outside of the port, find sufficient water depth, do your float-off there, and then you bring back your foundation, for example. If you were to do longer transits, like really a voyage where you want to transport, I don't know, the foundation from, I don't know, Vietnam or Singapore, let's say, to Taiwan, for example, that would not be acceptable. The range, because even if you restrict the tow to the route, to the seasons, the range of motions that you will be subject to would be too great. You would have cases of green water to check on your foundation. So you can manage a bit of overhang, like the case we gave for your foundation, like this. I think this you could go through with that. With this kind of overhang, you could do a long transportation even with half of your column going. You wouldn't do a lot more, basically. But after, it's about you demonstrating to the other stakeholders that the risks are okay, that it is safe. It's just that you might have to over-design your bridge and your tree-fastening, but then you're in a very different logic. You're trying to do a voyage that can be a few days or a few weeks. So the effort and what you're able to put into the sea fastening is going to be a lot greater. You might accept to actually have to weld the sea fastening to the foundation itself, because let's say small stoppers and these kind of things, it only works when you do short transportation for floater. If you do a voyage for mobilization a few weeks away, it's unlikely that you will do without welding the foundation. So you will weld the foundation to the bridge and or to the bar. And that's what restricts a lot the selection of this vessel, is the available breadth of the vessel. It's not the deck capacity. And here, in terms of strength, you will benefit from the side shell, which is fairly stiff, and you can try to align with a bulkhead, for example, a concrete bulkhead. But it is definitely concentrating more of the loads on the inner side of the column. And so you need to think about supporting not only at the columns, but you might need to have some supporting wherever the SPMTs are not, you're not in the world of SPMTs, you might need some extra supports at other locations, depending on how strong your pontoons are, for example, or how stiff they are. Any other question or something we can dig a bit deeper on? No?
Yeah.
Thea, any question from Thea?
No, right now.
Okay. Well, thank you, everybody. Thanks for the opportunity. Thanks for your attention.
好，就可能之后有问题会好。我已经用了过一次。
Next, have your questioning start.
Yeah. Yeah, if you have any question, any follow-up questions, feel free to reach out.
Yeah.
Thank you.
Are you American?
No, I'm French.
French?
Yeah.
Oh, so you will join the
PGF?
PGF.
Yeah. So SBM, we are based. I was based in Monaco, in the south of France.
Oh,
SBM.
SBN is not. It's
Equity.
not ABL group.
No. That was my previous company.
Okay.
And yeah, so that's where I've done. So I've done some transportation, installation, and lifting in oil and gas with SBM Offshore before, when I was in Singapore. When I started with Singapore, then I went back to France with SBM, and there I was working on the TNI of PGN. So all this lifting of modules, loadouts, and transportations, and all that. That's what I was doing for PGN. And after I took the lead of the new floater, the new generation of TLP for SBM, before I joined Longitude again in Singapore. So went back to France, back to Singapore again.
Oh.
But yeah, it was very interesting to be involved in this, because it was the first French project. Now there are 3 demos in the south of France. But at the time it was the first one.
Oh, cool.
I've been having it for a while.
Chris.
Yes.
Yeah. Have you been to Taiwan? This is the first time?
No, it's the fourth time.
Yeah. You mean Dr. John?
Yes.
Our boss.
In Energy Taiwan a couple of years ago. Then this year we came back. We had a big booth beside CIP. I mean, a bigger booth beside CIP. And then I came before that. The first time I came to Taiwan, it was to visit with my family.
Oh.
My wife loves Taiwan. She's Singaporean. So she
is Singaporean.
Yeah. So she liked traveling to Taiwan. So we went. Maybe we did 5 days in Taipei, and after we were more in the Taroko Gorge